How do you do? I'm Dr. John Sayce. Welcome to Urban Economics Advanced Topic number 7. In this video, we will develop a one input, one market, mill to port linear model by defining and summing input transport cost and output transport cost to get total cost. We will determine the optimal production location at either the input location, large I, or the market location, large M. Effectively, our choice of an example is an input-oriented firm with weight-losing production. We will determine that the optimal point of production should be at point large I, the input location. As we already know the solution, our discussion will concentrate on demonstrating why this is true. In our example, let us assume that this firm is a wine producer. Moving the input of grapes from the vineyards to a production site closer to the market involves the cost of transporting the grapes at a constant ton rate per mile. In contrast, if the wine is produced and bottled at the point of input, large I, the firm will incur a maximum cost for transporting their product. The closer to the market that they situate their production, the lower the transport cost for their bottles of wine. As with input, we assume that the transport cost per mile remains constant. In this graph, the slopes of the two lines imply that it is more costly per mile to transport fragile grapes with a high water content than it is to ship cases of the finished product. By summing the input transport cost and the output transport cost, we obtain total cost, the line in red. The location point at which total cost is lowest will be the optimal location at which to locate production, because total cost is lowest at point large M star, such that the highest output cost is at the vineyard. The firm would do best to crush the grapes and bottle the wine at the vineyard, location large I. For the mathematical side of our example, let's assume that we need 50 pounds of grapes to make one case, 12 bottles, each containing 750 milliliters of wine. A case of 12 bottles weighs 40 pounds. Given that 1 US, also known as a short ton, equals 2,000 pounds, 1 ton of grapes would allow us to produce 40 cases, 600 bottles of wine. These 40 cases weigh 0.8 tons, 1,600 pounds. Our basic assumption is that it costs more to transport 1 ton of grapes than 0.8 tons of wine. To keep our example simple, we assume P bar is the price per ton of wine at the market. A is the cost per mile to transport a ton of grapes. B is the cost per mile to transport a ton of wine. W is the wage rate. Large L is the amount of labor needed to produce 1 ton of wine. Large R is the price of enough grapes to produce a ton of wine. X is the distance grapes are transported. Y is the distance that wine is transported. And Z equals X plus Y, the distance from the point I to point M. Let large Q be the quantity of packaged wine in tons. Profit equals total revenue minus total cost, such that profit equals the total revenue minus material cost, minus labor cost, minus transport cost. In this equation, P bar times large Q equals total revenue, 1.0 RQ, which is the cost of the grapes. W large L large Q is the cost of labor, and large Q times the sum of 1.0 AX, the grape transport cost, minus 0.8 BY, the wine transport cost. To solve our location problem, let's first determine the optimal production quantity of the winery. We can express this condition in a number of ways, as the optimum occurs at the quantity that maximizes profit for the winery. Its marginal profit must equal zero. The difference between marginal revenue and marginal cost must equal zero, or marginal revenue must equal marginal cost. Taking our profit equation from the previous slide, we differentiate it in respect to the quantity in order to obtain marginal profit. If we rearrange our terms, we can express this condition as the constant price P bar in blue equals the first derivative of cost, which is 1.0 times the rent plus wage times the amount of labor plus 1.0 times the rate per mile times the number of miles that grapes are transported minus 0.8 times the rate per mile times the number of miles that the cases of wine are transported. However, this equation suggests that marginal revenue remain constant at P bar, and the only variables on the marginal cost side are A, B, X, and Y, where the condition exists that the sum of X and Y must remain equal to the constant distance between the vineyard and the marketplace. Therefore, the critical values for the determination of the optimal location are A, the rate per ton mile for grapes, and B, the rate per ton mile for wine. Both transport cost functions are linear, though inversely related. The one for grape transport is positive, while the one for wine transport is negative. Therefore, if 1.0A is greater than 0.8B, the optimal location for production of wine is at the vineyard. However, if 1.0A is less than 0.8B, the optimal location shifts to the market. One final comment. If 1.0A equals 0.8B, then the winery would be indifferent as to its location because any point between the vineyard and the market would suffice. This could only occur if grape rate equals 80% of the wine rate, or conversely, the wine rate equals 125% of the grape rate. In the next topic, we will consider a similar example, except that nonlinear transport costs determine one unique point for wine production. I hope this has helped you. If it has, please like, subscribe, and leave a comment for topics you would care to view. Thanks, and have a great day.